The time has now come to discuss the Coriolis Force, which is the second of the two fictitious forces that we have to deal with in rotational reference frames. In the last video we talked about the centrifugal force, which in spite of its complicated appearance is really just minus the centripetal force. The Coriolis force, however, is a little bit more complicated. If we look at it here, we can see that it depends on r dot. That is, it depends on the velocity of an object in the rotating reference frame. So if an object like this point P here is stationary in the rotating frame, there is no Coriolis force. And we can also see that it's going to be perpendicular to both the velocity and omega. So let's list some of these properties to make this explicit. Also, it only acts perpendicular to r dot because it has this form of the cross product, and for the same reason it is only acting in the plane that's perpendicular to omega. So the Coriolis force will act in this plane, but never vertically. We can look at the size of the Coriolis force. If we take the magnitude of the Coriolis force and compare to the magnitude of the centrifugal force, then we can see that, okay, it's 2m times the velocity, that's r dot in the rotating frame, times omega, roughly speaking. There could be a sign in there, we're just going to ignore that. This is an order of magnitude estimate. And then we divide by the magnitude of the centrifugal force. And remember now that this here is capital V, the velocity of the point that we're considering in the non-rotating reference frame. So it becomes V omega. So that's on the order of little v over v. In other words, the Coriolis force is, generally speaking, small compared to the centrifugal force. At least as long as this velocity is small compared to the velocity of the rotating reference frame. That doesn't necessarily have to be the case, of course. And this perpendicularity means that if we are moving in this direction here, then the Coriolis force is going to be perpendicular to the velocity. Now, to understand physically what the Coriolis force comes from, you really need to make a demonstration. Now, luckily, there are about 1 million YouTube videos that illustrate the Coriolis force or the Coriolis effect. So I'm going to show you pieces of a couple of them, and then you can decide if you like them or not. And if you don't, I'm sure you can find your own that you'd prefer that you find more explanatory.
Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right.
So in other words, the yellow line here, that's the path in the inertial reference frame. The ball is moving straight. There's no Coriolis force. The red curve here, that's the motion in the rotating reference frame seen from the vantage point of the people on the merry-go-round. And then you have the Coriolis force, so you get this apparent turn to the right.
Following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.
Okay, next I have a video from MIT. If you found this business with, the two simultaneous lines plotting the trajectories in the rotating and non-rotating reference frames, or rotating and non-rotating reference frames confusing, I have a video here from MIT that shows them separately. I'm not going to show the whole thing, but just a couple of pieces. So here we have a rotating platform, and these two guys are going to toss the basketball back and forth between them. And as you can see, when there's no rotation, nothing interesting happens. Whereas if it's rotating, well, then they have a much harder time catching the ball. Now we're going to move into a reference frame here where this is now shots from the non-rotating reference frame. As you can see, the ball is moving in a straight line. Right, and then we'll switch to the rotating reference frame with the camera mounted on the platform, and we now have a different effect. Right? We have the curved path. All right, so hopefully that gives you a physical feeling for what the Coriolis force is, where it comes from. But you also have to be able to use it mathematically, this particular formula, which encodes this effect. And that's what we're going to do in our example that we're going to treat next, which is the same one that we used in the case of the centrifugal force, namely that of freefall. So this is now something that happens on the surface of the Earth. That's going to be our canonical rotating reference frame. And we have an object here that is falling down, like we said, into a mine shaft, or maybe from an airplane or something. We'll neglect the forces of air resistance. So in that case, Newton's second law has the form that mass times acceleration is the force of gravity, mg0, plus the centrifugal force and the Coriolis force. Now, in the last video, we were able to show that we can take these two terms and bake them into a single term. So what this really becomes is mg plus f Coriolis. Maybe just say that g is g naught, like that, right? That gives us the effect of the Coriolis of the centrifugal force baked into an effective gravitational acceleration, and we now only have to worry about what the Coriolis force does. Okay, now we're going to pick a reference frame in order to work in. So what we'll do is we'll pick a reference frame where x hat is to the east, y hat is to the north, and z hat equals up. Right? This is our rotating reference frame. So if I'm going to show what that looks like here, this is the up direction, right? So that's z hat. And this is north, so that's y hat. And the x direction is now into the screen. And we also will have in here somewhere the position that we're going to work with, that's R. This is our local reference frame that's rotating with the Earth and that we're going to do the work in. So in this reference frame, we have, first of all, we're going to work with the velocities, and they're simple. They just consist of x dot, y dot, and z dot. But we also have that the vector omega, you can see here that it will have no x component, but it will have a y component and a z component, which depend on the co-latitude theta here. So it becomes 0, omega sine theta, omega cosine theta. Okay. Now if you want to calculate the Coriolis force, you have to calculate the quantity r dot cross the vector omega, and you should be able to show relatively quickly that that's equal to the following. That's just an application of the cross product, something you will need to be able to do yourself. So then if we write down now the Newton's laws here on component form, we get the following. And we can now see why it was convenient to work in this rotating reference frame, because now the force of gravity is only in the negative z direction. So the force of gravity is only present here, and all the other terms here are from the Coriolis force. So this term, and that term are the Coriolis terms. This is the gravitational force term. So this is a system of differential equations that we are supposed to solve. Now we can see here that this is actually a coupled system. X double dot here refers to both y dot and z dot. Y double dot refers to x dot, and z double dot refers to x dot as well. So in other words, this is a system of coupled differential equations. It turns out in this case it's linear, and we can actually write down a solution for it. But it's a little more involved than we would like to deal with at this stage. And it turns out that we can solve it in a different way, at least approximately, by noting that the Coriolis terms The Coriolis terms are actually in size much less than the gravitational terms. Which I put in blue here. Right? That again can be seen from the estimation we made up here. And we said that the Coriolis force is small compared to the centrifugal force, and we showed in the last video that on planet Earth actually the centrifugal force is small compared to g. So this is just a small perturbation, which means that we can use something known as perturbation theory. I'm not going to get into that in any detail here. We'll talk a little bit about it next semester, and it's something that will come up in quantum mechanics as well. All I'm going to say here is that what it involves is saying that, well, we can get pretty close to the correct solution by simply ignoring this small part, the Coriolis terms. They are a perturbation. And then we can take the solution that we get and use this as a starting point for finding a solution that includes the Coriolis effect. The best way to explain this is probably just to do it in order to illustrate how it's done. And then next semester we'll deal with the underlying math in a slightly more rigorous fashion. So the first step here is to just ignore big omega. So then you get the following systems of equation, which is much easier to deal with. Right? I'm going to say that r at point 0 equals 0, 0, 0. We're starting at the origin, and we're starting at rest. So that just gives us the solution, x. I'm actually going to call this x naught. This is the unperturbed solution. This is what's known as the 0th order approximation. So it's a reasonably good approximation of what's happening. Essentially, the particle will fall straight down and accelerate with g as the acceleration. We already knew that was going to happen. But then we have a small effect due to the Coriolis effect. And to see what that might do, I'm going to take this 0th order solution. I'm going to plug it back in on the right-hand side of this equation here and see what we get. So if we do that, we'll get x double dot equal to, okay, y dot, according to this solution, is 0. Z dot is not 0. So we will get, this is 2 omega yt, or gt times sine theta. And that's because, well, let's write this out explicitly too. If you take the time derivatives of this, it becomes just 0, 0, and minus gt. Right. So all I did was take this z, plug it in here, and I get this expression for x double dot. Y double dot remains 0, and z double dot remains minus g. So that's our new system of equation that we want to solve. And that's a lot simpler than this, but it gives you actually a good approximation to the solution here, as long as the x naught dot that you get is small compared to z dot. So let's solve this now. This is second order differential equation. We have x double dot proportional to t squared. So this will give us x equals 1/3 omega dt cubed sine theta. Just take the derivative of this twice, you'll get this. y is still 0, and z is still minus 1/2 gt squared. This is now known as the first order solution. And if we wanted to, we could take this first order solution and we could plug it into the right hand side here and solve one more time and keep going for as many times as you'd like, and each time get a better and better approximation to the correct solution. But we're not going to do this. This is a good approximation as long as we have that the magnitude of x dot is much less than the magnitude of z dot. That's really the only thing that that is required, because that's what we used, right, when we wrote down this equation as an approximation to this one. We said that, well, z dot is this, and compared to z dot, y dot is essentially 0. And same thing for x dot, and therefore this is a pretty decent approximation to this differential equation. So to see if that's the case, all we have to do is take the time derivative of x1 here and z1 and then compare their sizes. x1 here and z1 and then compare their sizes. So let's do that. So if you look at x1 dot divided by z1 dot, well, the 3 goes in front here and counts as the 1/3. So we get omega gt squared sine theta divided by gt. So it's omega t sine theta, which is going to be less than or approximately equal to omega t. Omega is 2 pi over 24 hours. So it turns out, if you do that, you get 7.3 times 10 to the minus 5 radians per second. So that means that the approximation is valid on the order of hours, at least. If I take this and multiply by a number on the order of 10,000, it's still pretty small. Right, and that's reasonable then to use this approximation, because object that you let release in freefall will typically only fall for a few minutes at the most, and for that reason we don't have to do anything more complicated in order to solve this equation. So what does this show then? Well, it shows that dropped objects do not fall straight down. There's some deviation. Now, if we want to turn x into a function of z, we can do so relatively easily with this solution. So we can show that t, just by inverting this, that's the square root of 2z over g, or rather 2 times minus z over g, because z is going to be a negative value. Let's make the absolute value. So t is the square root of 2 times the magnitude of z over g. And we can plug that into this expression here, and we'll find that x, the deviation to the side, is a function of distance, the distance fallen, with a little bit of work. Essentially, that just involves cancelling the g to the 3 halves that you get from inserting in here against that g. That's the only simplification we've made. So that's our solution. Now let's just say that we're dropping a stone into a 300 meter deep mine shaft. and that mineshaft is located at the equator. And that's where you get the maximum deviation at the North Pole or South Pole. Theta is 0, and we get no deviation at all. So we get then at x 300 meters, this is omega, (11.4 centimeters). So that's the deviation from the vertical. It is not particularly large, but it is something you can measure. 300 meters, by the way, is also the height of the Eiffel Tower, so there's something you could measure from there too, provided that you can drop something that's large enough and aerodynamic enough that you can ignore air resistance, which I would not generally recommend. Probably not possible either because of catch nets and things to prevent exactly that thing. But it's large enough to measure, and although not perhaps very practical. In the next video, we're going to talk about Foucault pendulums, I guess they should be pronounced, which is a more practical way of measuring the effect of the Coriolis force on the surface of the Earth.